All right, so yeah, excited to talk to you all today about the broad spectrum of carbon management technologies, specifically with an eye towards the carbon capture, storage, and removal implications for heavy industry. This is a key focus of the Biden administration's decarbonization work. And what I would like to do is share a little bit about the technology, actually walking back and providing even a higher level context than Tom shared just a few minutes ago, as well as what we are doing at the department to work with companies in industries like yours to advance technologies. Ultimately, this is your time though, so eager to hear your questions early and often. I'll encourage folks to raise their hands, jump right in. If I don't see folks, we'll ask Tom and Palomi to just slow me down, let me know folks have questions. So without further ado, we'll jump right in with just another word of introduction. The Office of Fossil Energy and Carbon Management at the Department of Energy is one of our applied offices alongside energy efficiency and renewable energy, nuclear energy office, et cetera. So we focus primarily around what I would call mid-TRL technology innovation. How do you get things that have come from the basic science world, are not yet commercially viable, and invest in their research and development to get them to that place where industry can scale them? I would say specifically, we had a restructure at the office. We have been working on carbon capture and storage for the better part of 2 decades at this point at DOE. We've consolidated all of that work into the Office of Carbon Management, which is the team that I lead. So we look at all of these pieces of the value chain. In particular, we think about two things in a little bit of a separate way. The first is carbon capture point sources. How do we mitigate the emissions directly from a whole range of industrial sources, whether it's power plants, fossil fuel, or biomass, as well as industrial facilities. And so when we think about industrial facilities, we think about energy produced at those facilities, but also the emissions inherent there. So think about burning limestone in order to make cement, other process emissions that might not be fossil fuel based, but nevertheless generate CO2 emissions. That is one area where carbon management is going to play a key role in industry and decarbonizing our manufacturing sector. The other place is carbon removal. Now, carbon removal, as Tom showed, can come in many different forms. Our office focuses on the technological components of that, but the secretary announced last year a carbon negative shot aimed at a department-wide initiative to scale all of the different carbon removal pathways. So we do collaborate with our colleagues across the office on all of those pieces. An increasingly large piece of our portfolio is also blue hydrogen production, essentially hydrogen produced using fossil fuels with carbon capture. That can fit into both the point source carbon capture and the carbon removal buckets, depending on the fuel and ultimate end use of that hydrogen. So going back to the diagram here, we actually think about carbon management in a very expansive way. And this is something that I think is a relatively new shift in the field. When I started working on carbon capture a decade ago, we were focused primarily on large stationary sources in the power sector. We were thinking about how can carbon capture and storage be scaled so that we would have low carbon coal power, low carbon natural gas power after that. I think the field has really shifted in the past few years as we've seen market forces really hamper coal's economic prospects in the power sector, as well as the growing importance of the industrial sector in meeting climate goals. Our industrial sector accounts for somewhere between a quarter and a third of all global emissions, depending on how you count the energy produced for that industrial production. And so that's at the scale of our power and transportation sectors. Figuring out how to do carbon capture at that diversity of industrial sources starts to really change how we think about carbon capture and storage. We are doing carbon capture at different scales, often at a much smaller scale than we have initially envisioned for fossil fuel power production. And we're introducing new types of solutions like direct air capture and storage, which fundamentally break the relationship between the place of the emission and the place of the storage. Direct air capture can be sited wherever it is feasible to do so. It does not have to be directly at a facility that is producing emissions. That's something that I think has an enormous benefit as we think about where we site facilities for carbon management. The reason that we're so excited to be working on this and talking with you all today is we are both at past one inflection point in the field. The bipartisan infrastructure law has put over $10 billion on the table already to support early of a kind carbon management demonstrations. But if our reconciliation deal going through Congress right now is able to get across the finish line, it includes today a significant increase in tax credits and incentives specifically for a wide range of carbon management technologies. We think that the reforms to the existing, what is known as the 45Q tax credit for carbon capture and storage will open up a wide range of new projects and increase the types of projects that are available to include things like smaller scale industrial projects, as well as smaller scale carbon removal and direct air capture projects. The funding that we have through the bipartisan infrastructure law is in two main flavors. The first is the cost share grants that DOE gives out historically through the Office of Fossil Energy and Carbon Management. Basically, we provide up to 50% cost share for building and operating carbon management projects, as well as new authority in the loan guarantee program to finance CO2 pipelines to transport CO2 from those sources to sinks. Okay. Happy to pause there. Let me just open up the floor to any questions about what DOE is doing in this space before I share a little bit more about where the field is and how it's evolving.
Technically, if folks have questions for Noah, you can, during the event here, you can either put them in Slido or in the chat function here. But any questions on the DOE activities?
Cool. Well, again, feel free to jump in early and often. What I'm showing here is a graphic from the Global CCS Institute that tracks basically every carbon management project that has ever been constructed and or has been proposed. What I want to highlight here is that there actually is a fairly deep bench of experience building carbon management projects. You'll notice that the x-axis goes all the way back to the 70s. And we have been doing carbon capture and storage continuously since that time. We have put over 100 million tons of CO2 underground since the 1970s, though I will say that the vast majority of that is for enhanced oil recovery, essentially using that CO2 to repressurize old oil wells to produce more CO2, to produce more oil. Obviously, this is not what we would choose to maximize climate impact, but it's the one largest use of CO2 that has remained economically profitable for the past nearly 50 years. In terms of where that CO2 is coming from, what you'll also notice here is that a lot has actually already happened in the industrial sector, and almost nothing has happened in the power sector, the direct air capture sector, as well as what I will call the kind of difficult to decarbonize heavy industry pieces. So cement, steel, iron, etc. Why we've seen this differentiation in projects is that as you get into the power sector and into some of the harder to decarbonize sectors, what ends up happening is the concentration of the CO2 in the waste exhaust stream for the industrial production gets lower. The lower it is, the more work is required to do the separation, the more expensive it is. That's just thermodynamics at work. And so what we've seen is that many of the early carbon capture projects have involved very high purity CO2 streams. When we think about natural gas processing, ethanol production, they have nearly pure CO2 that just needs to be dehydrated, have the water taken out of it. We don't need to do significant separation of other components in that flue gas. And so this is where we are focusing today, is how do we shift what exists in terms of carbon capture projects? We want to start being able to do the carbon capture on those difficult to decarbonize sources that have lower CO2 concentrations, because that's what ultimately is going to matter for climate. The high concentration CO2 sources are only on the order of 5 to 10% of all of the CO2 produced through heavy industry. It's going to require us to get really good at separating CO2 at much lower concentrations. Cement is somewhere between 10 and 25%, natural gas power between 4 and 8%, and ambient air is 400 parts per million, so 0.04%. So you can see that it gets increasingly challenging as we try and do different types of carbon management. To double click on this a little bit though, is we do have large scale carbon capture project demonstration history. Many of the projects that we have operated have been significant technical successes. They have been able to do exactly what they set out to do in terms of doing the carbon capture and storage. The reason that we do not have more of these projects, and why some of these projects like the Petronova power plant have closed down, is economics. There has not been a significant enough business case to do carbon capture at any reasonable scale. Again, we're posed for a potentially seismic shift in that market with the new tax credit package going through reconciliation right now. But it's, I think, an important history to know that we can do this. We have done it. The question now becomes, okay, how do we actually turn this into something that's not a series of one-off projects, but is something that we do consistently and has a real climate impact? Where we are focused in the administration is in exactly that place, the climate impact side of this equation. How can we start to find the sources that are going to likely have few alternative options for decarbonizing, and figure out where we can support early of a kind carbon capture demonstrations? Fortunately, there's actually a lot of clustering of these facilities around the US, and we have started to do the preliminary engineering and design studies for different carbon capture and storage projects. You can see here we've supported dozens of engineering analyses on different carbon capture sources, everything from direct air capture at the carbon removal side to the high concentration sources like ethanol and other types of chemical production. As we move into the, now we have captured CO2, what do we do with it side of the equation? This is where DOE actually has the longest history in doing the early stage research and stakeholder engagement. We have been working on developing and characterizing CO2 storage wells for over 2 decades. It's now a question of how do we start to move this from something that has a very deep history of research and early technical and commercial operation into something that can be widely done in a way that is safe and reliable and scales in the same robustness and with the same integrity for the environmental considerations and the CO2 storage that we've seen in some of these early projects. What we know is that today there have been very few sequestration wells that have been developed just for CO2 injection. That is, to capture the CO2 and not use it for enhanced oil recovery. We think that those types of dedicated storage wells are where the industry is likely to go into the future if it's to really unlock the maximum climate benefit of carbon management solutions. Fortunately, there's a number of well-developed resources to do that dedicated geologic storage across the US. Our high-level analysis suggests that there are orders of magnitude more storage capacity than we emit every year. So figuring out how to do the storage is something that we think is quite technically feasible. It now requires us to actually go out and prove that and scale it up in a safe way. The other thing that we're going to have to scale as we start to do carbon storage is transportation. In many cases, the industrial sources that emit CO2 are not located directly on top of places to store that CO2. Fortunately, we already have thousands of miles of CO2 pipelines. Most of those pipelines are taking CO2 from natural CO2 reservoirs and bringing them to oil fields to do that enhanced oil recovery, which in a context of a climate crisis is just a ridiculous thing to do, in my opinion, when you can capture that CO2 from an industrial source that is an anthropogenic source. So we're figuring out how are we going to start to build the same pipelines that we have used for oil production, instead to use them from anthropogenic CO2 sources in industry and increasingly in the carbon removal space, and transport that CO2 to where it can be stored safely for long time periods, and in a way that that is economically profitable. So again, we've been doing this for a very long time. You'll notice that Sleipner in Norway actually predates the DOE's work on this, I think by a year or two. But we've sequestered on the order of tens of millions of tons of CO2 in dedicated CO2 storage wells. And so this is something that we have confidence that we can do. And the natural analogs are, in fact, those CO2 domes, where there are billions of tons of CO2 that have been trapped underground in volcanic formations, essentially. The Bravo, basically these domes here in green show that CO2 can stay underground for millions of years if we find the right geologic formations. And again, this is not just a US phenomenon. There are ample storage resources around the world. We think we can store more CO2 than has cumulatively been emitted by humans and is likely to ever be emitted by humans. The question is now, how do we move from these very high level analyses into actually proving out some of this capacity in the same way that we sort of have much more rigor around proven oil and gas reserves around the world. I also want to transition here a little bit to say, while we have done an enormous amount of scientific work on this, and have come a very long way over the past 30 years, none of this is straightforward. There's a lot of complex geology involved in what we're doing. None of it is going to look radically different from what the oil and gas industry already does today in terms of actually fluid manipulation deep underground. Nevertheless, it does require very careful study and analysis because there are a wide range of different reservoirs that are well suited for trapping CO2. And what we need to do is make sure that we are doing detailed engineering designs so that we are thinking through all of the different dynamics of what happens underground. Speaking of, it's very difficult for me to communicate what exactly CO2 sequestration looks like underground, because again, this happens sometimes miles underground where the actual sequestration happens. But what gives you a sense of what's happening here is the CO2 at a microscopic level is finding its ways into pores in rocks that already contain water and is getting trapped in those pores at a very micro scale. And so over very large volumes, that CO2 adds up. And over time, what happens is that CO2 actually reacts with alkaline materials in the rocks. CO2 is slightly acidic and turns into stone. And so this is an example of one of the types of rocks that has reacted with CO2 and has trapped that CO2 not in a supercritical gas liquid state, but instead in a solid rock formation that essentially locks it away. Putting all of these together, we now know that there's a lot of confidence in our ability to store CO2 at geologic timescales. This is incredibly important because when we pull fossil fuels out of the ground, we know that they would have stayed underground on the order of millions of years without human intervention. And so what we want to show is that when we are injecting CO2 underground, there is a very small risk of leakage or reversal. And we have the certainty with a lot of the geologic data and analysis that we have. So let me pause here. I know it's a lot of technical content, but want to open the floor for any questions.
Noah, we're actually getting a number of questions over in Slido right now, which covers the whole range, really. For the time being, I would suggest maybe if you could just keep moving and we'll just hold the Q&A to the end. I haven't seen anything that's super contextually appropriate.
Okay. Well, I can't see what's happening on the Slido right now with sharing screen, so we'll just run through this and follow up shortly.
Yeah.
Okay. So we've actually talked a little bit about this, so I'll actually go through this a little bit more slowly. But let me step back a second here, which is the conversation that I've presented so far has been technical and increasingly scientific as we get into some of the details here. What we care about is not just the technical aspects of carbon sequestration, and carbon capture, which we are pretty confident about after the decades of experience that we do have. What matters to us equally is that projects happen in a way that advance the administration's goals beyond the climate math. That this administration has stressed over and over again the importance of rectifying environmental injustice, about creating high quality jobs that support families, about protecting the environment beyond climate, and doing so in a way that creates economic opportunities for communities that are and have been fossil dependent and have relied on fossil fuel extraction or use for the past decades or even century. All of that is to say is that we are thinking a lot about that at DOE and have done a number of analyses to try and answer some of those key questions. How can we make sure that when we do carbon management projects, we are doing them with the highest integrity to all of those other societal considerations and impacts, if you will? We also recognize that when we hear from environmental justice stakeholders, carbon management projects are usually greeted with a fair amount of skepticism, if not outright rejection. We listen to those concerns very deeply and are only interested in doing projects in communities and supporting projects in communities that really want to do them. That said, we are working with those same communities to share as much of the information that we have already with them so that they can have an independent and fair picture of what carbon management projects are likely to bring, and that they can have the resources that they need to be able to engage actively in any sort of carbon management project siting or development process. We want to make sure that there is clear and robust information available to not just communities where carbon management projects are potentially going to happen, but also to help the project developers themselves understand what we see as high quality engagement and empowerment of those communities to be involved in and benefit from those projects, and make sure that we are protecting communities and the environment from any unintended consequences. So I know we're kind of running out of time here. So I'll just say that we've thought about a lot of different pieces of this equation, kind of what happens when CO2 migrates underground, how does that potentially affect groundwater, how does it potentially mobilize other types of hazardous materials like heavy metals and potentially bring those into water, how does it potentially have seismic implications like we've seen in the fracking industry in recent years. And we've just done a wide range of modeling and analysis here to try and understand all of those different geophysical risks. Much of that work is incorporated into the existing regulatory framework here. And so the main place in which that underground sequestration is regulated is through the Environmental Protection Agency's water program. Specifically, their underground injection control. There is a dedicated class of carbon sequestration wells called Class 6. This is actually a fairly new characterization of Class 6 is only about a decade or so old at this point. We've had more decades of the other classes of underground injection, whether it's CO2 to make oil, all sorts of chemical and water injection underground is regulated under this provision. And so Class 6 is fairly new, and it's something that does have an enormous amount of data requirements to ensure that projects don't create any risks to groundwater. And there's accompanying analysis about how we make sure that the CO2 stays underground for the climate benefit that we want it to achieve. And so I'll just note that there's a lot of discussion today about Class 6 permitting on both sides. Basically, how do we make sure that it incorporates all of this information and that project developers are not incentivized to kind of disclose less information or do a shoddier job in the permitting, while at the same time, how do we make sure that these projects can move forward in a timeline that makes them feasible from a financial perspective. So this is all stuff that the Department of Energy supports. Again, EPA is the ultimate regulatory authority on this issue, but we have a deep history of collaborating with them on this and are working across all of our agency partners thinking about CO2 storage offshore. Again, not EPA, but we're working with the Department of Interior. Just really quickly, wanted to touch on CO2 pipelines. I know I mentioned that we do have a large history of this today. We also are working closely with CO2 pipeline regulators. This is through the Department of Transportation. The safety aspects of those pipelines are regulated there, but there actually is not any federal authority to regulate interstate CO2 transportation in the way there is electricity production or fossil fuel transportation across state lines. So it's actually a state by state regulatory process.